Hi everyone, this is Anushka and welcome to my channel in Economist. So in the previous video, we have started off with the concept of specification error or specification bias, where we have discussed the five possible specification error that any researcher or econometrician can commit in the research work or any kind of project or thesis, right? So we have in detail explained what is omission of relevant variable, what is inclusion of unnecessary variable, wrong functional form, error of measurement, and incorrect specification of the stochastic error term. If you haven't watched that video, I will give the link in the description and also in the I tab button. Please check that video out before going into this video, right? So today, what we are going to do, we are going to discuss about the consequences of this first specification error, which is the omission of relevant variable. If in your model mistakenly you omit one of the important variables, that is statistically significant variables, what will be the consequence for that? That is what we are going to discuss in this video, right? So let us quickly start with that. So firstly, we will define our true model. Our true model, suppose, looks like this: yi equals to beta 1 plus beta 2 x2I plus beta 3 x3I plus ui. For all I say varies from 1 to n. Suppose this is our true model that we should use in our purposes. But what is the model we actually use? What is the incorrect model? What is the incorrect model that we work with? Suppose yi equals to alpha 1 plus alpha 2 x2I plus gi for all I equals to 1 to n. Now, can you observe the omission of relevant variable here? Suppose x3 is a relevant variable in our true model, but due to some mistake, due to it might be our carelessness or it might be lack of data, we have completely excluded the variable x3 while undertaking our research work. That is why an incorrect model appears, which looks like the second model. Now, if this is the scenario, what will be the consequences? So let me write x3I is the omitted variable. x3I is the omitted variable here. Then what will be the consequences? The first consequence will be the left out variable, that is this x3I can get correlated with the included variable, which is x2I, which basically means R23. The correlation, this is R23 is basically the correlation between x2 and x3. It can become non-zero. And now if this becomes non-zero, it basically indicates that there could be the presence of multicollinearity in your model, right? There could be the presence of multicollinearity. In several previous videos, I have in details explained what is multicollinearity. If you haven't watched those videos, please, check out the playlist. I'll give the link in the description. Please see the, concept of multicollinearity. Then you will understand what I'm talking about. Now see, if you completely exclude this variable x3 in your original model, only x2, you include only x2, you completely eliminate the variable x3, what will happen? It is very likely that the variable, the left out variable, which is x3, this left out variable will get correlated with the included variable x2. And in multicollinearity, what happens is that several explanatory variables becomes correlated with each other. Then the problem of multicollinearity may arise. This is the first consequence of omission of relevant variable, right? I hope this point is absolutely clear. Now let's come to the second consequence. Second consequence is alpha 1 cap and alpha 2 cap. What is alpha 1 cap, alpha 2 cap? See, these are the estimators of the incorrect model. The estimators of the incorrect models, they will be biased. They will be biased as well as inconsistent in nature. They will be biased as well as inconsistent in nature. What does that mean? It basically means that if you take the expected value of alpha 1 cap, it will not be equals to alpha 1. If you take the expected value of alpha 2 cap, it will not be equals to the original population parameter alpha 2. And also, as n tends to infinity, inconsistency means what? This is bias basically. If the expected value is not equals to actual population value, it will give you the biasness. And inconsistency means as your n will tend to infinity, this bias will not disappear. The bias still exists, right? Bias still exists. That is why the estimators are not only biased, they will also be inconsistent in nature. So this is the second consequence. Let us see the third consequence. The third consequence is the disturbance variance. This is the disturbance or the error variance, what you call. Let me call it error variance. Sigma cap square, which is the error variance. This quantity is also be incorrectly estimated. This will also be incorrectly estimated. And this will be the third consequence. Now, what is the fourth consequence? The fourth consequence will be even if x2 and x3, these are the two explanatory variables in your model, even if x2 and x3 are not correlated, even if they are not correlated, alpha 1 cap is still biased, even though alpha 2 cap is now unbiased. So what does this basically means is that we have already, taken a look at the scenario when x2i and x3i are correlated with each other. If they are correlated, then the possibility of multicollinearity will arise. This is the first consequence we have discussed. But what will happen if they are not correlated? Suppose x2i, the excluded variable x2i and the included variable x2i, they are not correlated with each other. Even then you will see alpha 1 cap. Alpha 1 cap is the estimator of the intercept parameter, right? Estimate of the intercept parameter that will still be biased. Although the slope parameter that is the alpha 2 cap, slope parameter estimator alpha 2 cap will now become unbiased. And in this video, we'll prove this thing. We will prove this thing. So hold on. I'll show you why this happens. So this will be the fourth consequence. Now see the fifth consequence. The fifth consequence will be the confidence interval. Ci, I am not writing entirely. Ci is the confidence interval, and the hypothesis testing will give misleading results. About the significance of the estimated parameters. So basically, if you are testing the hypothesis like this, alpha 2 is 0 versus alpha 2 cap, alpha 2 is not equals to 0. Suppose you do this kind of hypothesis testing, this will genuinely give you misleading results, because see, your error variance is not correctly estimated. If the error variance is not correctly estimated, your residual sum of square is also not correctly estimated. All the subsequent things that you will compute, the t statistic that you will compute, everything will give you misleading results. So basically, alpha 2 cap, the variance of alpha 2 cap is what? Variance of alpha 2 cap is simply sigma square upon summation I from 1 to n. x2i minus x2 bar whole square. This is the variance. This is the variance of the slope parameter. This will also be bias estimator. This will also be bias estimator of the variance of the true estimator beta 2 cap. So see, in the original model, the estimator is this. This is the true estimator, which is true population parameter beta 2. So the estimator will be true estimator, which is beta 2 cap. And here you are replacing that with alpha 2. In the incorrect model, you are replacing that only with alpha 2. Now you see that the variance of alpha 2, this will be a biased estimator if you omit the relevant variable x3 from your model, then this will be a biased estimator of the variance of the true population parameter. So if the variances are also not correctly estimated, if the error variance is also not correctly estimated, the t statistic that you will compute, that will also be incorrectly estimated, as a result of which confidence interval and hypothesis testing, whatever you do with your model, it will give you misleading answers. So this thing we will show you in the next video. The proof will be given in the next video. As of now, let us prove the fourth property, that in general alpha 1 cap and alpha 2 cap will be biased estimators. But if we can show that x2 and x3 are not correlated with each other, then alpha 1 cap will still be biased, but alpha 2 cap will now become unbiased. So let us quickly prove this thing and then we'll finish off with this lecture. So let us start with the model. So our model is this: yi equals to beta 1 plus beta 2. So basically we are proving the second consequences and the fourth consequences all together, right? This is the proof of second and the fourth consequences. So beta 1 x2i plus beta 3 x3i plus ui. This is the true model. Now what we do, we firstly find out the deviation form. To find out deviation form, we need this y bar. Beta 2 x2 bar plus beta 3 x3 bar plus u bar. Now if you subtract yi minus y bar, what do you get? Beta 2 x2i minus x2 bar plus beta 3 x3i minus x3 bar plus ui minus u bar for all I. So what can you say from the first term? This yi minus y bar is small yi. Deviation form, many times we have discussed. x2i minus x2 bar is small x2i. Beta 3 x3i minus x3 bar is small x3i plus ui minus u bar. So this is the model in the deviation. True model in the deviation form will look like this. Now what we do, we will form the three normal equations. If you remember, the first normal equation can be obtained if you take the summation I from 1 to n on both the sides. This will give you the first normal equation. For the second normal equation, you have to take the sum, but you have to also multiply with x2. So x2i yi, if you do this in the left hand side and the right hand side, you'll get the second normal equation. And for the third normal equation, this is I from 1 to n. And this is I from 1 to n. Here you have to multiply by x3i. x3i and yi is already there. So in this way, you have to form the three normal equations. Let me show you how to do this. So the first normal equation will be simply this. Take summation on both sides of this particular equation. If you do that, this will be beta 2 summation I from 1 to n x2i plus beta 3 summation I from 1 to n x3i plus summation I from 1 to n ui minus u bar. So this will be the first equation. The second equation, multiply by x2i and yi is as it is. So if you do that, beta 2 summation I from 1 to n x2i square plus beta 3 summation I from 1 to n x3i square plus summation I from 1 to n x3i ui minus u bar. This will be the second equation, and the third equation is this. x3i into yi. Here you have beta 2 summation I from 1 to n x2i x3i plus beta 3 summation I from 1 to n x3i square plus summation I from 1 to n x3i ui minus u bar, right? So this is the first equation that you have, this is the second equation that you have, and this is the third equation that you have, right? Now what we will do, the next step would be to divide both sides of equation 1, divide both sides of equation 1 by summation I from 1 to n x2i square. If you do this, what you will get? Numerator remains the same, summation x2i yi, and in the denominator, this x2i square comes. I'm dividing both sides by summation x2i square in the first equation. So, sorry, the first equation, sorry, this is the second equation, right? Yes. This is the second equation. Pardon me for that. So this equation, basically this equation, we are dividing both sides by this summation x2i square. So if you do that, first term is beta 2, second term is beta 3, summation I from 1 to n. Then you have x3i, x2i upon summation x2i square. And then summation x2i ui minus u bar. And in the denominator, again, you have I from 1 to n x2i square, right? This will what you will get. Now the left hand side. What is the left hand side? Left hand side, if you remember, it is just the substitute of alpha 2. It is just the substitute of alpha 2. So you can give it another name B12, suppose I write B12. This is just an alpha 2 cap substitute. We'll again substitute it with alpha 2 cap later on. But see, as of now, just name it B12. Then this beta 2 remains the same. Then you have this beta 3. Now what is this? What is this thing? This is, if you remember, this is the partial regression coefficient of 3 and 2, right? I have made a separate video on partial correlation, partial regression coefficient, multiple regression coefficient, all these things are done in a separate video. Again, I'll give the link in the description. Please check the concepts out if you don't know already. So this entire thing is B32 is the partial regression coefficient of x2 and x3. And then the remaining terms remains the same. I from 1 to n ui minus u bar summation I from 1 to n x2i square. Now all you need to do, take expectation on both sides of this equation and then you will get the required answer. So let me do that. Expectation of B12. And on the right hand side, you have expectation of beta 2 will be beta 2. Because in the original model is consistent with all the assumptions from multiple linear regression model. So unbiasedness holds in the original model. But in the incorrect model, this unbiasedness is not holding. That is what we are trying to prove. Now beta 3, and here you have B32 plus. Now the next term, you have to put the expectation on ui minus, let me show you, on the ui terms only. So expectation of ui minus u bar summation x2i square, right? So as I have told you, you can, instead of beta 1, 2, you can substitute it back to alpha 2 cap. See, this is the estimate of alpha 2 cap from the, so in the incorrect model, you have only x2 as the explanatory variable and y is the outcome variable. And if you have, if you consider it to be two variable CLRM, right? If you consider it to be two variable CLRM, then you will get this. See, the estimate of the slope parameter in the two variable scenario. That is exactly what I have written here. This B12 is nothing but the estimated value of alpha 2 cap You can consider the incorrect model, which is a two variable regression model where you have only one dependent variable yi and one independent variable x2y. You can consider it as this: uh, y equals to alpha plus beta x plus epsilon. If this is the case, what is beta 2 cap? It will be summation this upon summation x square, basically, right? This is the exact form that we have written here. The covariance of xy upon variance of x, right? This is simply, you can write covariance of xy upon variance of x, and that is the exact thing we have written here in this way. So it is nothing but the estimator of the slope parameter. Here our this beta is equals to alpha 2 in our incorrect model. Let me show you the incorrect model once. This is the incorrect model. See here, the slope parameter is alpha 2. So alpha 2 cap will be simply covariance of yi x2y upon variance of x2y, and that is what is given here. Right? That is what is given here. That is why we can substitute this beta 1 2 as alpha 2 cap. And what about the right hand side? So this first portion remains the same, beta 3 b3 2. Now what about this? What about this entire thing? So what is expectation of ui? Expectation of ui is 0. What is expectation of u bar? Expectation of u bar is also 0. So this entire thing, expectation of ui minus u bar will be simply expectation of ui minus expectation of u bar. So this entire thing will be 0. So this entire expression becomes 0. Since the numerator is 0, the entire expression becomes 0. And you are landed up with this particular expression. Now, can you tell me what does this signify? What does this signify? This signifies that this term here is simply an extra term. This beta 3 b3 2, this term is simply an extra term here, and this will make alpha 2 cap a biased estimator. Alpha 2 cap is a biased estimator of beta 2. So the original population parameter is beta 2. So if alpha 2 cap is biased, then expectation of alpha 2 cap should be equals to only beta 2. But it cannot be so because you are getting an extra term here, which is the amount of bias. Here the amount of bias will be amount of bias. Amount of bias is given by this extra quantity, so, right? Amount of bias will be this extra quantity here. That is due to the presence of this extra quantity, this alpha 2 cap is a bias estimator of beta 2. Now to make it unbiased, so this is the first consequence. See, this is the consequence number 2, that alpha 2 cap will be biased. This is how you have to prove this. Now we have said that if the correlation between x2 and x3 is 0, if there is that is not correlated, then what will happen? That is what we need to show here. Alpha 2 cap will be unbiased, for beta 2, will be unbiased for beta 2 only if the bias becomes 0. Only when the bias becomes exactly equals to 0, that is beta 3 b3 2, this term becomes 0. See, the bias is beta 3 b3 2. So once this term becomes 0, alpha 2 cap will become an unbiased estimator of beta 2. Now when this term will be 0, so it can be 0 in two ways. Either beta 3 can be 0, or it can be that b3 2 can be equals to 0. Right? These are the two possibilities. Now if beta 3 equals to 0, what is the issue? What is the issue? If beta 3 equals to 0, there is no specification error at all. Let me show you the models again. See, if this beta 3 is exactly 0 in the true model, if beta 3 is 0 in the true model, then this x3 term is not there at all, right? X3 term is not there. If beta 3 is exactly equals to 0, then this entire thing is 0. So in the original model also, x3 is eliminated. X3 is not present in the original model, and then there is no difference in the true model and the incorrect model. Because see, in the incorrect model, so we have we have omitted the x3 variable, but in the true model also, if you say beta 3 equals to 0, then the two models will be exactly identical. There will be no specification error at all, right? So this possibility is not there. So no specification error. If beta 3 equals to 0, there is no specification error which basically means the two models will be exactly identical. Two models will be exactly identical, which is not a possibility. Because here we are dealing with specification error, right? Here we are dealing with specification error. So no specification error condition, we must exclude this possibility, right? We have to exclude this possibility. So beta 3 can't be equals to 0. So the only possibility is that B32, this quantity has to be exactly equals to 0. This will be the right approach. What is B32? B32, as I've told you, it is summation I from 1 to n. It will be simply x2i, x3i upon summation x2i square, right? X2i square. Now in this numerator, the numerator of this term is what? It is simply the covariance. It is simply the covariance between x2 and x3. And the denominator will be the summation x2i square, whatever it is, right? The covariance between x2 and x3. Now, if this beta 32, if it has to be 0, the numerator has to be equals to 0, right? If this beta 32 has to be equals to 0, it can only happen if the numerator is 0, because see, the denominator is the sum of squared terms. Sum of squared terms can never be exactly equals to 0. Even if it's 0, it doesn't make any sense. So this denominator can't be equals to 0 because it is in the ratio form, but the numerator can be exactly equals to 0. So to make beta 32 exactly equals to 0, we need covariance of x2 and x3. Covariance of x2 and x3 exactly equals to 0. And if covariance of x2 and x3 exactly equals to 0, it in turn means R23, that is the correlation between x2 and x3, that has to be exactly equals to 0. Because correlation is what? Correlation is covariance between the variables upon sigma x into sigma y. This is the formula of correlation. Now, if the covariance itself is 0, then the correlation coefficient will also be 0. So R23 will be exactly 0. So this basically proves our statement. See the statement that we have given previously. Let me go back to the statement. See, alpha 1 cap and alpha 2 cap are in general biased, and in general they will be inconsistent. This we have proved. But in the fourth consequence, we have said even if x2, x3 are not correlated, this is the last thing that we have proved. Our x2, x3 are 0. If they are not correlated, then alpha 1 cap is still biased. We haven't proved anything about alpha 1 cap. It is still biased, but alpha 2 cap is now becoming unbiased. That is what we have proved, right? That is what we have proved. If R23 is 0, if R23 is 0, see here, let me go back. So see, alpha 2 cap will be unbiased for beta 2 only if the bias is 0. So we are checking the condition, when will this alpha 2 cap will be unbiased? This can only be unbiased when the bias is 0, which means this criteria. And we have shown that this beta 3 cannot be equals to 0 because it will lead to no specification error. We must exclude that possibility. So the only possibility is that beta 32 equals to 0, which has given us the criteria that R23 equals to 0. So what we can conclude from all these things? What we can conclude, if R23 is equals to 0, alpha 2 cap is an unbiased estimator, of true population value, true population parameter, beta 2, this is there, but alpha 1 cap is still biased and inconsistent. Right? It's still biased and inconsistent, and this is how you have to prove this entire thing. Right? R230 means x2 and x3 are uncorrelated. Basically, x2 and x3, these two explanatory variables are uncorrelated only when alpha 2 cap is a unbiased estimator of beta 2, but alpha 1 cap is always, in any situation, it is biased and it will be inconsistent, right? So I hope you liked this video. This is all I wanted to share in this video. In the next video, what we will do, we will go into the other consequences and we will try to prove this particular thing. So we haven't gone into the error variance and the variance, how these variances are, incorrectly estimated. We haven't gone into that in this particular video. So we'll be touching upon that in the next video. So stay tuned for that. As of now, if you like this video, give me a thumbs up and do subscribe to this channel in Economist. That will give me immense motivation to continue making such useful videos for you. So stay tuned for the next video and thank you so much for your time.